Welcome to the third lecture on conductors, and here we are going to discuss very extensively about sheets, or to be more precise, about infinite sheets. Infinite sheets of charge. Infinite sheets, as in both of these sheets are very large, incomprehensible with respect to the present distances, and these are very large sheets, and we are trying to look for the magnitude, direction, and all those things about field lines due to this charge sheets. Now I have drawn two diagrams. There is a reason for it. The left one is a conductor, and the right one is a non-conductor. The left one is a conducting sheet, whereas the right one is a non-conducting sheet. And let's say I gave charge Q to the non-conducting sheet. I gave charge Q to the non-conducting sheet. How are the field lines going to be? Let's say the total charge is Q, so fields are going to be in both directions away from the charge. Why away? Simple reason, the charge is positive. Due to a positive charge, the field lines are totally away from the charge. If there were a negative charge, the field lines would have been towards the charge, so you will understand the difference there. And the magnitude of field lines is very simple. It is equals to sigma by 2 epsilon naught. Or if you want to replace sigma, you can very easily say that it is equals to Q upon 2a epsilon naught, where a is the area and Q is the charge. You can very well see that the fields are also inside the material of the non-conducting sheet. You can see that. And on the left side also, the value is obviously sigma by 2 epsilon naught, or we can say Q upon 2a epsilon naught, where a is the area of the conductor. Although a is very large, likewise Q is also going to be very large, but okay, very large upon very large can give us finite values, so we are not going into that right now. Now we do the same thing with a conductor. I give it a charge Q, and when I give it a charge Q, let's say I give it on the right face. Let's say, assuming I give it on the right face, then I'll have fields from the charge, because we know that the property of a charge is to emit fields away from it if it is positive, and there will be fields here also. It's taking a lot of time to draw anyways. So there will be fields here also, but you can see the problem here. What is the problem here? Can anyone guess? The problem is very simple. The problem is that there can be no fields in the material of the conductor. Inside the material of a conductor, field lines must be equals to 0. But this thing seems to be a bit contradictory. How? If we have a charge here and there are field lines on both sides, that is the property of the charge, we are also saying that the field lines inside should be equals to 0. So how do we get rid of this contradiction, or how does a conductor deal with this kind of a contradiction? So we move on to the next page to see that. So this is our infinite conductor. First I want you to focus at the left. The conductor is obviously infinite, infinity, infinity. And as I told you that I gave it a charge on the right face, very large amount of charge on the right face, that was Q. And then due to Q, that's inevitable, it's going to happen, there are going to be fields. There is no stopping that. But what do we know about the material properties of a conductor? We know that a conductor has a lot of free electrons, and the free electrons inside the conductor will obviously experience force. They will experience force opposite to the direction of the field. So as you can see that inside the material the field is towards left, so the electrons will experience force towards right, and you will see an accumulation of negative charge on the right side. Likewise, since the conductor was electrically neutral, there would be an accumulation towards left side. And due to this particular accumulation, there will be field lines from the induced positive to the induced negative. And as you can see, all those field lines will tend to cancel out the original white field. So this was your original field and this is your induced field. The induced field inside the conductor tends to cancel out the original field. And something else or something more interesting is happening. On the left face of the conductor, the diagram is going to be very dirty now. On the left face of the conductor, you can see a positive charge appearing. And on the right face of the conductor, you can see the combination of positive and negative charges. So a lot of these positive charges are going to cancel out a lot of the negative charges are going to cancel out the positive charges. So we want to look at it, how the final thing looks like. So this is our final thing here. And as I said, I gave it a charge Q. Okay, so let me put it in white. Right, I gave it a charge Q. Let's say that half of the charge, exactly half, accumulates on right side, Q by 2. And the other half of the charge, that was Q by 2 obviously, accumulates on the left side. That you can see happening from the left diagram also. From the left diagram, you can very easily see that on the left side there is a positive charge. On the right side there is a combination of positive and negative charges which will obviously reduce the positive charges. So the other half Q by 2 appears on the left side. Now let me divide our conductor into 3 zones. Let's say this is zone 1, this is zone 2, this is zone 3. Zone 2 is obviously the conducting zone. You have to take notice of that. It's a conducting zone and the field inside the conducting zone theoretically should be equals to 0. But now we want to know if it is practically achievable. Let's look at the charge on the right, Q by 2. The field lines due to charge on the right would be towards right, of course. They will also be towards left, of course. Or let me do, what do I do is I divide it into, let's see, I divide it into 3 parts. So the field inside will be towards left and then there will be a continuation in the left direction also, like this. And what is the value of field that is going to be? The value of field, you know, every one of you know, the value of field is going to be sigma by 2 epsilon naught, and this time sigma is not made up of Q. You must understand, sigma is made up of Q by 2. So it is going to be Q by 4a epsilon naught, and this side also it is going to be Q by 4a epsilon naught. Right. Now let's talk about the charges. Let's talk about the charges on the left. These charges, Q by 2 on the left. Due to these charges also, I'll show it with a different color. There will be a field away from the charges, showing it with green as you can see. There will be fields away from the charges this way. And there will be fields away from the charges this way. Now what do we understand from this? We understand that inside the conductor there are equal number of white fields as well as green fields which are opposite in direction. So all of them will get cancelled out pairwise. So we will have the cancellation of fields here. And on the right side there will be an addition because the white fields and green fields are in the same direction. So the green fields will be Q by 4 epsilon naught and the white fields are Q by 4 epsilon naught. So what is the net field that you are going to get? Let me draw it here. The net field that you are going to get is Q by 2a epsilon naught. Likewise, on the left side also you are going to get q by 2 epsilon naught 2a epsilon naught, and in the conducting material the field is going to be 0. So what a conductor does is simply this. Let's draw the conductor here. So if I give this conductor a charge q, and the job is of this conductor is to make fields inside the shaded region to be 0. The easiest thing for the conductor to do is simply to divide its charges q by 2 and q by 2 equally on both faces. Now due to this q by 2, let me draw the left q by 2 with a different color, q by 2 in green. Now due to the blue q by 2, the field is q by 4a epsilon naught, and due to the green q by 2, the field is again same direction, q by 4a epsilon naught. So the net field becomes q by 2a epsilon naught. Likewise, due to the blue q by 2, the field is on the left, field is q by 4a epsilon naught, and due to the green q by 2, it is q by 4a epsilon naught, and then you combine it and it becomes q by 2a epsilon naught. That is the total field. But inside the conductor, inside this region here, the field is towards left due to the blue charge and towards right due to the green charge, so you will always have a cancellation in pairs, and the field inside the conductor becomes equals to 0. So this is a common question that is generally asked, and these sheets are considered to be infinite. I'm not drawing infinite, just consider them to be infinite, and we give them some charges. Let's say we give them this one, I give it a q charge, I give it a minus 2q charge, and I give it a let's say 4q charge. Now the question that is generally asked is this: find the charge arrangement on the faces of the sheets. It's a very bad handwriting, but I'm speaking it so you can understand it. Find the charge arrangement on the faces of the sheets. So there are 6 faces, as you can see. There could be like phase 1, there could be phase 2, there could be phase 3, and then phase 4, and then phase 5, and phase 6. So we have 6 faces in total, and we want to find out the charges that are appearing on all these faces. Now, as you can see that inside the material of the conductor, whatever we do, the field is going to be 0. There is no denying that. And whatever charges are being rearranged, howsoever they are being rearranged, are under this condition that the field in the blue region, the blue shaded region, is going to be 0. So how do we distribute it? Let's see. First of all, we assume, since we don't know what is going to happen, and you cannot simply say that it is going to be half and half, because right now there are other charges also. If there was only one sheet, you could have easily said it's half and half, but it's not half and half in this case. So please don't start thinking on that it is half and half. Now let's say that I have a charge q here, small q, and since the charges are conserved obviously, so the rest of the remaining charges will go to the left face, and now I have a charge q dash here. Now about this q and q dash, there is something that we can do. What we can do is this: we can draw a Gaussian surface that passes from inside the material of the sheets. This is our Gaussian surface. As you can see, the red surface. Let me name this Gaussian surface. Let's call it A, let's call it B, let's call it C, and let's call it D. Now we all know that the field between the plates can be towards right or towards left, that we don't care. But in the conducting material, the field is always going to be 0. In the conducting material, the field is always going to be 0. So if we have a Gaussian surface, we can divide our Gaussian surface basically into 4 parts. So the first surface is AB surface, and in AB surface you can see very easily that the field lines are basically either parallel or anti-parallel to the surface. So the flux through AB surface will be equals to 0. Likewise, the CD surface, the flux through CD surface will be equals to 0 because the field lines are either parallel or anti-parallel to the surface. None of those field lines ever cross the surface. Going on, then we have the AD surface, and the flux through AD surface is going to be 0 simply because it is a conductor. The surface is inside a conductor. And likewise, the flux through BC surface is going to be 0 for the same reasons. 0. Let me remove it. 0. For the same reasons that BC surface is also inside the conductor and AD surface is also inside the conductor. So what do we understand from this? We have 4 surfaces, and from all the 4 surfaces the flux becomes 0. So the total flux, the net flux is equals to 0. And if the net flux equals to 0, we have charge enclosed is equals to 0. And this leads us to the most interesting result in this problem. If the enclosed charge is 0, you can see what is the enclosed charge. You can see the enclosed charge inside the surface is basically q plus q dash. And if it is equals to 0, we can have q dash is equals to minus q. And this is what leads us, or what brings us, to our most fundamental results of parallel plates. Charges on facing plates, facing surfaces of the plates. Let me write it here. Surfaces of plates are equal and opposite. So coming back to our problem, it has become lot of things have been written down here, so I'll change the pace soon, but I want you to focus here. So this is plus q and minus q, and inside this Gaussian surface we must know that the charge enclosed should be 0. If the charge enclosed is 0, we have q dash is equals to minus q. And if q dash is minus q, if q dash is equals to minus q, we must know that on facing surfaces of the plates, facing surfaces, that is in this case surface 2 and surface 3, they are facing surfaces. Likewise, surface 4 and surface 5 are also facing surfaces. So if we have a charge q double dash here, we are definitely going to have a charge minus q double dash here. So on the facing surfaces, the charges are equal and opposite. That is the first fundamental thing that you need to know. So back to the problem again. We knew that the charge here was q and here it was q minus q. And we came to know that charges on the facing surfaces are equal and opposite. So this is definitely going to be minus q. Now if you apply conservation of charge, like this, if minus q appears on the left side, then plus q will appear on the right side. So plus q will appear on the right side, and there is already a minus 2q there. So the net charge that is going to be there on the right side is definitely minus 2q plus q. And again, applying the principles of facing surfaces, here the charge is going to be 2q minus q. And again, applying the principle of conservation, if you have 2q minus q on the left side, you are definitely going to have minus 2q minus q on the right side. And there was already a 4q there, so if you sum them up, what are you going to get? 4q, you have 4q minus 2q, that is definitely going to be 2q plus q. So let me revise it again, and I know it can become confusing. So we started from here, we took the charge here as small q, and the remaining went here by conservation. Now there are two things that are happening here, conservation and facing surfaces thing. So on facing surfaces thing, the charges must be equal and opposite, that we know. And on a single plate, the charge must be conserved. So if there is a minus q here, there will be a plus q here. and also the minus 2q that was already given, that will also be present. So the net charge on the left side, I haven't named the surfaces. Okay, so let me name the surfaces: 1, 2, 3, 4 and 5 and 6. Okay, and 6 on the surface 4. On the surface 4, if the charge is minus 2q plus q, then on the facing surface 5 there will be an equal and opposite charge, that is 2q minus q. Now again, using conservation, if there was 2q minus q here, there will be minus 2q minus q here, added with the 4q that was already present, so we will get 2q plus q. And we are using two principles here in distribution. The first one is the conservation of charge on each plate, and the second one is that the charges on the facing surfaces should be equal and opposite. But this arrangement is not complete. As you can see, it is very much visible. We need to find out this small q. Only when we have found out the small q, we are going to get all other values, all these values. So what do we do then? We simply apply the principle of conductors. We take a point here, and we know that inside the conductors the field is always going to be 0. Due to all the charges, the net field is always going to be 0. That is the basic fundamental of distribution. The charges will distribute such that the net field at any point inside a conductor, like this one here, the red point, is going to be 0. Now let me name the charges because it is going to be confusing. So I'll call this charge as A, I'll call this charge as B, I'll call this charge as C, this one as D, this one as E of course, and this one as F. So I have 6 charges, and I want to find out the combined field. I want to really focus here, I want you to really focus here. I want you to find out the combined field due to all these 6 charges, that is A, B, C, D, E and F, at this red point, here. Let's assume that the charge small q is positive. Okay, so if the charge small q is positive, the field due to small q is definitely going to be away, so I'll call this as EB. Also assuming that q minus q is positive, this one here, this one is also positive, assuming that, so field due to q minus q is also going to be away from the charge, so this will be called as field EA. Now coming up to the charge C, this is negative, so field due to the negative charge is always towards, so I'll call this as EC. Coming up to the charge D here, what are we going to assume? This is minus 2q plus q, so we'll take it negative, we'll take this charge as negative, so field due to a negative charge is definitely towards, so we'll call this as ED. And if this is negative, then this is definitely positive, and if this is definitely positive, the field due to a positive charge is definitely away, so I'll call this as EE. Don't get confused, the first E is the field and the second E is the name of the charge. And finally, to the final charge, we are assuming this one to be positive. If we are assuming this one to be positive, so this EF is definitely going to be away, like this, EF. So at point P, let me draw this again. At point P, there is a field EA like this, there is a field EB like this, and then there is a field EC like this, and then there is a field EE like this, and then there is a field ED like this, and then there is a field EF like this, EF. And we can see that there are 6 fields towards left, 3 fields towards left, 3 fields towards right, 6 fields in total. Now there are some that are going to get cancelled out. Which are the ones that are going to get cancelled out? For example, the ones from B and C. As you can see, field due to B is towards left and field due to C is towards right, and the magnitude of charges are equal and opposite. So the magnitude of charges are equal and the fields are in opposite direction, we can definitely have EB and EC cancelling out. Likewise, the field due to D and field due to E, they are definitely equal and opposite, and you can see they are opposite in direction. Field due to D is towards right and field due to E is towards left, so there is definitely a cancellation there. So D, I'm sorry, there is a cancellation, D and E, there is a cancellation there. So what are we left with right now? We are left with field due to A, let me draw this in white, field due to A and field due to F. And both these fields should cancel out. Should cancel out means we know that the point, this point or this point is inside a conductor, so the field due to A and F should cancel out. If the field due to A and F should cancel out, then there is one most important thing to understand, that the charge at A must be equals to charge at F, and they must have same signs. They must have same signs. Why same signs? Charge due to field due to A must be away, so towards right. Field due to F must be away, so towards left. So they must have same signs. So Q at A equals to Q at F, and that gives us Q minus Q equals to 2Q plus Q, and finally we get small q equals to minus Q by 2. This is the value of small q that we have calculated. So every time are we going to do this complex calculation, or there is a shortcut to it? The shortcut is, there is a shortcut, and the good news is that the shortcut is very simple. You just have to take care of the distribution. So let me change the distribution somehow. So let's say this is 2q and this is q and this is minus 3q, an entirely different kind of a distribution. All of them are capital Q, so I'll remove this. So this is q, and I just have to take care of the distribution. So I'll take care of the distribution how? So let's say this is small q. By conservation, this will be 2q minus q. By equal and opposite on facing surfaces, minus q. This will be q plus q. This will be minus q plus q. And since there is minus q plus q, there is minus q plus q here. You will definitely have plus q here, and minus 3q added with it. So the final result on the right side is going to be how much? Minus 2q plus q. So this is your arrangement. Now the shortcut is simply this. You have to consider the first charge and you have to consider the last charge, and you must understand that the first charge and last charge will be exactly equal even in terms of the signs. So what we are going to do is this: 2q minus q is equals to minus 2q plus q, and 4q is equals to 2 times small q, so you get small q is equals to 2q, and this is your arrangement. Way smaller than what we did in the previous things. But so if you don't understand the idea why are the first and the last ones equal, I want you to go back, rewind this video and see it again. Now since we have found out the value of small q, it becomes very easy to find out the arrangement. This is 2q, of course. This will be 0, of course. This will be minus 2q, 3q, and this will be definitely minus 3q, and this is going to be 0. So first is equals to last, and that is your final arrangement of charges. There are more complex questions to this, and for that we are going to move on to next page. So this is another question, and you can see there is a bit of a complexity here, and I would like to introduce the complexity by saying it. This distance is d, first distance between first two plates, and the distance between the second and the third plate is, let's say, 2d, and there is a switch. You can see there is a switch here. This is a switch, your switch, and the question says that find the final arrangement, I'll write it in short, final arrangement of charges on faces after the switch is closed. After the switch is closed. So after the switch is closed, and the question wants you to find out the charges appearing on each face. So let's close the switch first. So closing the switch here, right. Now as you close the switch, you know that there is a transfer of charge that takes place between plate 1 and the plate 3. So you can say that the charge on plate 1 is not definitely conserved, the charge on plate 3 is not conserved, but the charge on combined A1 plus 3, charge on combined plates 1 plus 3 is conserved. So this is very important to understand. If there is a transfer that is taking place between 1 and 3, I cannot say that charge on 1 is Q and charge on 3 is 4Q. I can say that, I can just say that the sum of charges on 1 and 3 is 5Q. That's all I can say, because there is a transfer that is taking place. So let's carry on with our distribution. So this was Q obviously, and this was minus Q. And the second plate is not connected to anything. As you can see, this is your second plate, is not connected to anything, so the charges will be conserved. So it will be minus 2Q plus Q, like that. They will also be equal and opposite, so 2Q minus Q, like that. And here on the surface, the leftmost surface, let's say it's Q dash, so on the rightmost surface it will also be Q dash. Why equal? Do you remember? Let me remind you. We know that the field at any point P on the conductors inside the material of the conductors will be 0, and when we solve that, we get the first charge is always equal to the last charge, both in magnitude as well as sign. So this is your arrangement, but as you can see, it's not a complete arrangement, simply because of the fact that there are two variables. There is a small q and there is a q dash, some of which we can try to solve using conservation. We know that charge on plate 1 plus 3 charge is conserved. So we take the charges on 1 and then we take the charges on 3 and then we try to add them up. So the charges on 1 is, please see, the charge on 1 is left side q dash, right side q. So charge on 1 is q dash plus q, plus charge on 3 is, please see, what is the charge on 3? That is q dash again, plus the inside charge, that is 2q minus q, and that is the sum total of charges on 1 and 3. And do you remember what was the sum total of charges on 1 and 3? It was equals to 5q. So when you solve this, what do you see? You can see easily that minus q and plus q get cancelled out, that is small minus q and small plus q get cancelled out, and you get 2q dash is equals to 3q. So q dash is definitely out, it is 3q by 2, that is 1.5q. So we know what q dash is. We know what q dash is. It is 1.5q. It is also 1.5q. You must understand, capital Q is not variable. It was something that we initially gave to the plates. But the problem still remains. And what is the problem that remains? The problem that remains is simply this, that we still have to find this small q in order to complete our distribution. So this is your charge arrangement, intermediate charge arrangement, but we know that we still have to find out this qn, this minus q, and this and this. And we also know something else. We know that these two are connected. The first and the third plate are connected by a switch. Now what happens when you connect two things by a conductor? When you connect two things by a conductor, they acquire same potential. Acquire same potential. So when you connect two conductors by a wire or something like that, they acquire same potential. So if this is 1, this is what 2, this is 3, we will have potential of 1 is equals to potential of 3. Or we can also say that potential of 1 minus potential of 3 equals to 0. If there is a field here and there is, let's say, a field here, and we know that the distance here is d, and we know that the distance here is 2d, the potential difference is equals to 0. And let's call this field as field E1 and let's call this field as field E2. Now what is field E1? Or due to what reasons will there be a field E1? Now I'm going to be fast on this one. I need you to really focus. Due to the charge 1.5q and 1.5q, the field in the region between plates and 1 and 2 will be towards right and left. So they will get cancelled out because both charges are positive and both are in opposite directions. So due to 1.5q, the field will be away, and also due to 1.5q, the field will be away. So they will get cancelled out. Now let me remove this. Due to charges minus 2q plus q and 2q minus q, the field will be something like this. Due to minus 2q plus q, it will be towards, and due to positive 2q minus q, it will be away. So it will again be cancelled out because the charges are equal and opposite and they will have fields in opposite directions. So this field will also get cancelled out. Now all we are left is this. The field E1 is only due to the charges plus q and minus q, and this you can remember on face value basis. If I have two plates, no matter what the charges are outside, the field inside will only be due to q and minus q. This you can take on face value basis and you can use it as you like. There are generally no exceptions to it. So the field in this region, the field in the facing surface region is only due to the facing charges. The field in the facing surface region is only due to the facing charges. So what is the field E1? I am going to solve it here. The field E1 will be due to two reasons, due to plus q and due to minus q. Due to plus q, it will be q upon 2a epsilon naught, and due to minus q, it will also be q upon 2a epsilon naught. So your net field E1 becomes equals to q upon a epsilon naught, the sum of the fields due to plus q and minus q. Likewise, the field due to E2 will be also due to minus 2q plus q, that is minus 2q plus q upon 2a epsilon naught, and also due to 2q minus q in the same direction, that is 2q minus q upon 2a epsilon naught. Okay, some of you might get confused here. I am assuming this charge to be positive. So if I am assuming this charge to be positive, the field due to the charge will be away from the charge. And if this charge is positive, I am repeating again, if I am assuming this charge to be positive, this charge is definitely going to be negative, and field due to a negative charge is always towards the charge, towards the plate. So what is E2 going to be? The E2 is going to be, that is minus 2q plus q. Let me write this, it's very okay. So where do I write it? Okay, I write it outside, best way. The field E2 is going to be minus 2q plus q upon a epsilon naught. This is your field. So basically you have two fields, E1 and E2, and there is a lot of assumption here. First of all, I don't know what is charge small q. I don't know if it is positive or negative. I only know this. What do I know? I know that on facing surfaces, the charges will be equal and opposite. So I have taken this charge to be positive, the field will be away, and this charge to be negative, the field will be towards. Likewise, I have taken this charge to be positive, field will be away, and this charge to be negative, the field will be towards, and in both cases you can see the fields are getting added up. So in the first space, this space here, the field is q by a epsilon naught, and in this space here the field is minus 2q plus q by a epsilon naught. Now how do we find out the potential difference? How do we find out the potential difference between 1 and 3? So first we jump from 1 to 2 and then we jump from 2 to 3. That is the technique that we are going to use. So let me, okay, so this is right. Okay, so okay, here. So I am going to jump from, first of all, I am going to jump from 1 to 2. So when I am jumping from 1 to 2, the potential difference is E1 into D. And when I am jumping from 2 to 3, the potential difference is basically E2 into 2D. Why 2D? 2D is the distance between the plates. And what I am doing here is I am simply using the formula dV equals to minus E dot dr. You remember the formula? And I'm ignoring this minus sign here. I'm simply ignoring the minus sign. I just simply want the potential differences. So potential difference at the first jump, the potential difference at the first jump between 1 and 2 is E1 into D, and the potential difference at the second jump between 2 and 3 is E2 into 2D. And this is your total potential difference. And why it is your total potential difference? Because E1 and E2 are in the same direction. I want you to understand here, because E1 and E2 are in the same direction, and that is why I am using a plus sign. So now when I have jumped twice, I have simply find out the potential difference between 1 and 3. And what was the potential difference between 1 and 3? I want you to remember here, the potential difference between 1 and 3 was equals to 0, right? So the potential difference between 1 and 3 will be equals to 0. Now I know what is the value of E1. It's written right here. So the value of E1 is q by a epsilon naught into D, plus the value of E2, it's written right here. So the value of E2 is going to be minus 2q plus q upon a epsilon naught into 2D equals to 0. And you can see there are some common things that can get cancelled out, that is d by a epsilon naught gets cancelled out, and what do you get? You get q minus 4q plus 2q, 2q equals to 0. So 3 small q is equals to 4 capital Q. So small q equals to 4 by 3q. And this is the value of small q that we have got. And when we have got the value of small q, we can find out the charge. So this was your plates. This was your plate 1, this was your plate 2, this was your plate 3. The charge on this plate was obviously how much q. This was the charge on this plate was minus 2q, and the charge on this plate was 4q, right? And we had found out small q. We had found out small q, that was 4 capital Q by 3. So we are going to write down all the charge arrangements that we know of. So this was 4q by 3. This is minus 4q by 3. And if you add 4q by 3 to minus 2q, so it will be 36 minus 2q by 3, and it will be 2q by 3. Now I want you to see if the charge was actually conserved, if the charge on plate 1 and 3 is actually conserved or not. So let me mark it out. This is the charge, these are the charges here, so that you don't confuse it with the yellow portions. Sorry. So what is the charge on plate 1? Charge on plate 1. The charge on plate 1 is 1.5q plus 4q by 3. And what is the charge on plate 3? The charge on plate 3 is 2q by 3 plus 1.5q. And if you add them, charge on 1 plus charge on 3, what do you get? So 1.5q plus 1.5q is 3q basically, and 4q by 3 plus 2q by 3 is basically 2q, so you get 5q. So see, it is conserved. How do we know it is conserved? Because when we started, the charge on the plates was q and 4q. What was the sum? 5q. And what is the sum still? It is 5q. So the charge is conserved. But the charge is not conserved on individual plate 1 or individual plate 3. The charge is conserved between plates 1 and 3, the combined system of plates 1 and 3. That's an interesting thing. There's a second interesting thing that I want you to note. Initially, the charge on plate 1 was Q, and finally the charge on plate 1 is the sum of these two, right? So what was the charge transferred through this wire? If somebody asks you, okay, so how much charge was transferred through this wire, right? So the charge that was given by this wire, Q given by plate 1, is the initial value, that was Q, minus the final value, that is 1.5 Q plus 4Q by 3. You can solve it if you want. That will be equals to Q minus 3Q by 2 plus 4Q by 3. So that is, so Q minus 17Q by 6. And what is 17 minus 6? So that you get is minus 11Q by 6. So this much charge, minus 11Q by 6, was transferred from plate 1 to plate 3 in the process. Okay, so now we come to the final part of the chapter. If somebody asks you that there is a switch that is connected to the earth, and we know very well what earthing means. Earthing means the potential at of a certain object or a conductor becomes equals to 0. That is what earthing means. So if we connect the switch, the last plate, that is plate 3, let me number them 1, 2 and 3. The plate 3 will be earth and the potential of plate 3 will be equals to 0. So after earthing, V3 will be equals to 0. Now the question simply asks is find the charge arrangement. Find the charge arrangement. What is your charge arrangement? So first of all, this is earth. Now if this is earth, you must understand that the charge on 3, that is plate 3, is not conserved. This plate can very well take charges from earth, or it can give its charges to earth. So there is a free transfer that can take place between the plate and the earth. So the charge on this plate cannot be 4Q, and that is a problem. It cannot be 4Q because there has some transfer taken place. What do we do now? Now we know that we know very well that the potential of this plate 3 is equals to 0. And we also know that the potential at infinity, if you go large distance from it, the potential at infinity is also equals to 0. Now if the potential here and the potential at infinity both are equals to 0, so there would be no field between this point and infinity. If there are continuous points and there is no other charge in between, there will be no fields between these points and infinity. So what will happen is this, that there must be no field here in this region. In this region we can say that there is no field here equals to 0. Now what should we do? What should we do to make field in this region equals to 0? The simplest thing that we can do is to make the charge here 0. Now you will understand it in a bit why have I made the charge 0, but let me continue with the explanation. If the charge here is 0, then the charge on the leftmost face must also be 0, because we know that the charges on the leftmost and the rightmost faces are always equal. So that is that. Now if this is 0, so this one becomes Q, and this one definitely becomes minus Q, this one becomes minus Q, and this one becomes Q, and this one obviously is 0, the last one is 0. Now how does this thing ensure that the field in this region is 0? So there is a very easy way to understand that the field in this region is 0. How does this thing ensure that the field in this region is 0? So we must understand that let me draw the region. So this is region 1, this is region 2, this is region 3, this is region 4. So in region 1, The field is only due to this and this. Why is that? Because these are equal and opposite, their fields will get cancelled out, and these are equal and opposite, their fields will get cancelled out. So field in region 1 is only due to the leftmost and the rightmost charges, and hence it is 0. Likewise, the field in region 4, the rightmost region, is also 0 because the field is only due to the leftmost and rightmost charges. The field in this region is only due to this charge and this charge, and there is no field due to these two or these two charges because the net fields will get cancelled out. You can very well see here that the charge here is Q, the charge here is minus 2Q, which was initially given. Q is also conserved, minus 2Q is also conserved, but the charge on this plate is Q, but initially what charge did we give it? We gave it 4Q, right? So there was some transfer that took place, and what was the transfer that took place? The transfer that took place was 3Q to the earth. 3Q to the earth. So the charge on first plate is conserved, the charge on second plate is conserved, the charge on third plate is not conserved, and the charge that was transferred to earth was 3Q. So there are more questions to it, more complicated questions that I will discuss in different videos, but this marks the end of conductors. Thank you.